Welcome back to the course on textile finishing. We have covered some distance on the crease recovery finishing. We are going to continue with that for some more time. Let us see what do we do. We have learnt number 1 that the crosslinks formation is facilitated by a pad dry cure process. Why? Drying is important because it reduces the possibility of migration of chemicals to the surface. We have checked that the crease recovery angle would increase if the concentration of the cross-linking agent is increased in the bath. As a result, the actual cross-linking increases, the add-on increases, and if that happens, then we will see that the crease recovery angles will also improve, which is our main motive. We have understood the Rebenfield's hypothesis, which talks about why viscose and cotton behave differently when in dry and wet condition and when they are cross-linked. So, formation of cross-links according to the Rebenfield hypothesis in cotton is going to decrease the strength, while in the case of viscose it will increase the strength, and we know because the crystallinity of cotton is much higher compared to that of viscose, and therefore, the non-uniformity in the case of cotton only increases, which does not help in retention of the strength, and the strength decreases. So, most the cases, in almost all cases, the strength is going to go down because of the reasons, the losses, the strength losses due to the acid presence, due to the temperature of curing, which is could be high, and of course, cross-linking based on which fiber we are talking about. The stiffness generally would always increase because the intermolecular movement is going to be restricted, which obviously helps in recovery of creases, but it can make the fabric little stiffer. So, we accept that, which can be measured by bending length. Also, we have concluded that the abrasion resistance also would go down after cross-linking. Let us look at some of the calculations before we go further, and I like to see how you respond to this. Let us say somebody has said that what would be the concentration of chemical in the bath liquor. So, there is a bath liquor which contains the chemical could be, from our purposes, let us say cross-linking agent, and for some optimization process it has been concluded that you want 2% add-on on the fabric. So, now the question is, obviously you know the difference between add-on and you also know the difference between the content. So, we are talking about add-on, all right. So, what we are looking at is if 100 gram of fabric has been used, then it will become 102 grams. Therefore, 2% add-on is required. So, what it is asking is the concentration of the chemical required in the pad liquor. Okay. We know already how much do we want on the fabric. So, there are two processes which we had already said that one could be an exhaust method. Okay. And somebody wants to now say, well, this is the question, please try and answer this question. How do you answer this question? Well, let me ask you again, when somebody says concentration, what does it mean? You have to define a unit. So, what is missing in this question is the unit. You do not know what unit people are asking for. Is it in percentage or is it in grams per liter? So, that has to be defined. So, this was a missing link. So, you can't obviously answer this question. So, let us see, we say, well, we are looking at the concentration in grams per liter. Okay. So, can you answer this question now? What will be the concentration in grams per liter of a chemical in the bath liquor if 2% add-on is required on the fabric? Can you answer this question now? Can you answer this question? No? Well, you can't still answer the question because there is some data still missing. One must say what is the ml ratio. ml ratio. It has not been defined. So, if ml ratio has not been defined, how can you calculate the concentration? All right. So, let us say we define the ml ratio now as 1 is to 100. You know what does it mean? That means 1 gram of fabric, if it is to be treated, then you are looking at 100 ml of liquor, right. Can we solve the question now? Exhaust process means whatever is actually in the bath gets exhausted onto the fabric. So, how much you should take in the bath? What should be the concentration? Now, we are talking about in grams per liter. Yeah. You can still not answer this question. Why? Because you want to still know what is the exhaustion percent. Based on the data, previous history, one would know, because all these reactions in some way or the other are equilibrium processes. There may not be 100% reaction, there may be only 90% reaction, the rest may be only in the bath. 90% goes into the fabric, 10% remains in the bath. So, this can alter your calculations, right. So, let us assume here the exhaustion is 100%. It is a very ideal situation where everything which is in the solution finally goes to the fabric. Then what would be the concentration of the chemical in the bath liquor? Now, you can calculate, now you have everything. So, you want 2%, that means 2 by 100, and the ml ratio is 1 is to 100, but you want in liters and not in percentage. So, what we are looking at 1000 ml versus this is 100, and so this comes out to be 0.2 grams per liter, right. Is this clear? Let us say we have another case where we say we want to do by padding. The question still remains the same, and let us say the concentration required also here is also in grams per liter. Now, can you calculate? Can you calculate? What is missing? What is missing? Missing is wet expression. So, in the case of padding, we need a parameter called wet expression. You can squeeze the mangle more, you will have let wet expression, you can reduce the pressure, more wet expression. So, based on the wet expression, the amount of liquor is going to be picked up. Now, you are quite sure what an expression is, right. So, what will be the case? You want 2% add on, that means 100 gram of the fabric will take 100 gram of liquor. So, if you consider this as 100% expression, this value, then the concentration of the pad bath is close to 20 gram per liter, 20 gram per liter. In the previous case, it was 0.2 grams per liter. What I wanted to tell you was that the concentration of the chemicals in the padding systems is much higher compared to the exhaust system. You get this? All right. Now, let us go further. So, today we will talk about catalysis and catalysts. So, remember we said that for cross linking, other than the cross linking agent, you require a catalyst. Okay? So, we will learn little more about it. Obviously, we are talking about at the moment cellulosic systems, fibers, fabrics, and we are looking at the N-methylol compounds. Right? We have not changed that cross linking agent. So, if you remember, for the N-methylol compounds, these reactions are acid catalyzed. So, you require some acid catalyst, and it happens via a carbonium ion formation. So, that is the way the reaction with cellulose, that is the hydroxyl group of cellulose, takes place. Which type of link is formed? We talked about the link. So, link is ether. Is that clear? This is what we had already done. Remember? Yeah. So, let us see what types of catalysts are suitable for affecting this type of a cross link, this type of a covalent bond. So, the various types of acids that can be used. What becomes important for us is that which one are going to be helping us more. More means what? That there is efficient cross linking. Yes, of course, that we would want. We would also want the losses due to the acid itself be less. We may want that the losses due to curing temperature may be less. How can a catalyst help? Well, catalyst may help you to reduce the curing temperature. Catalyst may make sure that the fabric degradation is less. If that happens, then we can say that the optimization in terms of selection of catalyst may have been done. So, there are various possibilities as far as the catalysts are concerned. These could be free acids, that means the acid is immediately available, which means the proton. The latent acids, which become acid at a certain time or maybe certain temperature. There are others are metal salts which are different, which are something like Lewis acids. Then people have also suggested use of mixture of salts and acids, which can in some way help. Then we have a category of catalyst called the phase separation catalyst. There, during this process of, let us say, curing itself, there is a separation of phase. That means a solid could be precipitated at some given point of time. So, the phase gets separated. self-limiting type, that they actually almost get eliminated themselves at the end of the day. That means after the process, after the reaction is over, or chlorohydroxides. There are many others also. We will not discuss everything. If you are interested, you can always go down the literature and keep looking at various things that people have tried over the years. So, let us talk about free acids. The free acids are the ones which very easily release the proton. You remember, in the mechanism of cross-linking, there is a proton which is required, which helps you to form the carbonium ion, right. So, free acids are, because they are called free, because they can very easily give you the proton, all right. Some of the examples are from the mineral acid groups, HCl, sulfuric acid, nitric acid, these are the examples. They can be used, they will immediately in water start giving you the proton, and the proton can start participating. So, are you getting alarmed? Try thinking of using sulfuric acid with cotton at 150 degrees, where the concentration obviously would be quite high. There will be a lot of degradation. So, the mineral acids in the pad dry cure situation are not very suitable, because they will help in cross linking, but the fabric deterioration can also take place. And so, maybe we can think of something else. Organic acid, they also are Bronsted type acid, give proton. The only thing is they are known as weak acids. Weak acids. The mineral acids were strong acids, right. So, they are weak acids. So, obviously, their efficiency is going to be low, but they will be little less harmful to the fabric. Okay. Acetic acid people may not use, because it evaporates by the time the cross linking itself takes place. So, people may use other organic acids like citric acid, tartaric acid, which would remain intact during the process of cross linking, that is at the curing temperatures. We expect the losses to be less, all right, compared to the mineral. That is why you can understand why people will try different things. Then there are other category which is also known as latent acids. That is, the acid is not immediately available, like when you dissolve in water, the water does not really behave like a strong acid, but at the time of curing it can happen. Some of the examples can be from the salts, ammonium salts. So, ammonium salt like ammonium sulphate or ammonium chloride, they are water soluble, but they do not behave like, let us say, HCl or a sulfuric acid, all right, they remain. Then the still weaker versions could be ammonium salt of citrate, citric acid, tartaric acid, and that would mean that they will be available at a later stage, not in the beginning. Therefore, you will say, well, if any bad effect of the acid is there, it will only happen during the curing stage and not while it is being dried, while it is being padded, while it is in storage conditions, right. So, much before drying, during drying, the degradation will be less, but when curing happens, they will become active. So, the time required or time available for degradation obviously is going to be much less. Do you agree? So, they are going to be better in that sense. The mechanism, what is the mechanism? Obviously, The ammonia is one interesting gas which will come out during the process, and the acid will be liberated, and that acid is going to work like a Bronsted acid and give you the cross link. But we have tried to avoid the initial portion when it does not behave like a strong or a weak acid in that sense. There are other examples which are not ammonium compounds, but they are metal compounds, metal salts. Some of the examples of the metal salts that we have been using for cross-linking are, let us say, magnesium chloride, zinc chloride, zinc nitrate. These are some of the interesting compounds. There are others also. We can take aluminum salts also. The important thing is they act as Lewis acids, that is by electron transfer and not really release a proton. Okay. That is one of the differences that we have. So, what would be the mechanism of these things, because there is no proton now? So, what happens? Well, something like that we can expect. So, this is our cross-linking functional group N-methylol. Instead of proton, we have, let us say, a metal ion. This metal ion gets associated under the conditions that we have, almost in a similar manner. And then the metal hydroxide separates, and then again you get back the carbonium ion, in the presence of heat and of course, our cellulose hydroxyl group. Similar reaction can now take place. A proton comes out, and what you get is a link which we remember as a acid ether link is created. So, instead of water, it is the hydroxide of the metal that gets separated here. The mechanism still remains the same as the carbonium ion mechanism. So, it works, and people found that this type of a thing is able to retain strength much more, is quite efficient and works. Now, the only question is which type of metal ions that may use, which type of metal salt they may like use. Then what happens to this MOH? This is interesting again. Now, the MOH can react with the proton that has been generated during this process, and again you can get a metal ion and water which can evaporate and so on and so forth. That means metal ion is back. So, it is not that we are consuming metal ion. So, the MOH which was generated here gets converted to metal ion again. Of course, there was a possibility that this proton can directly react with this as well, can react. So, it has got two ways the efficiency is increasing, either the proton reacts with the hydroxyl group and again goes back to the same mechanism, or it can react with the metal hydroxide and create a metal ion. Efficiency of these is pretty good, strength losses are less. So, this is a mechanism, you understand. The interesting thing of course is, well, you can use aluminum based compound, magnesium based compound. What the difference between them is the oxidation number, like magnesium for example has got 2, aluminum for example has got 3 oxidation number, therefore reactivity. So, it has been seen that the activity of the metal salt is high if the oxidation number is high. So, aluminum is very highly active compound, but it is actually too active and people may or may not like to use it directly. Aluminum chloride is very reactive, very active, and so the efficiency may be more, but you can still see some possible degradation because it is pretty fast. People have generally stayed with magnesium compounds. Zinc could have worked the same way, only thing is zinc these days comes in toward the heavy metals, and so environmentally people may prefer magnesium, which is a lighter metal compared to let us say zinc. Aluminum could have been preferred very easily, but it is very highly active. So, directly chlorides of aluminum are not suggested for use. Another interesting suggestions which people have tried and used is mixtures of metal salt that we have just been talking about and hydroxyl acids, or we say hydroxy acids. Metal salts are good catalysts working as Lewis acids, right, and we have seen their mechanism, which is interesting mechanism which makes them more efficient, and based on the oxidation number of the metal, the reactivity will be high, the activity will be high, the activation will be better. So, efficiency of those compounds, the metal salts is good. But interestingly, if you use mixtures of metal salt plus carboxylic acids, then there is some synergistic effect. But these carboxylic acids are alpha or beta hydroxy substituted carboxylic acids. Okay. These carboxylic acids are alpha or beta substituted hydroxy acids, all right. So, they are not ordinary carboxylic acids. So, there is something interesting. How do they act? They act by decreasing the ionization constant of the metal salt. Now, you remember in the metal salts, the metal ion is the important one. So, by doing this, it happens. So, becomes easy. That way, they increase the efficiency of catalysis, okay, and thereby reduce the temperature of curing. Now, you will obviously like it. Let us say if the temperature of curing reduces from to 120 degrees centigrade from 150 degrees centigrade. So, that is a saving in energy, that is one part, but more importantly damage, thermal damage to the textile also going to be very less here. So, by decreasing ionization constant, they increase the efficiency of catalysis and help thereby reduce the temperature of curing. So, in some sense we can say that they give us synergistic effect. Okay. So, they help each other, that is what the synergistic effect. So, one can use various compositions like 40-60 or 50-50 or 60-40, and one can get lot of work has been done on this, but that only says that if you use metal salts and carboxylic acids, you will be able to increase efficiency, reduce temperature. So, some of the examples of these are, let us say, glycolic acid, which is a simple acid, okay. So, this is a hydroxy acid. Other is a citric acid, if you remember citric acid. This is tricarboxylic acid compound. And there is a hydroxyl group here. So, it becomes a hydroxy acid. Okay. So, these are hydroxy acids which are either the hydroxyl group is either in alpha position is this, or in a beta position, and such type of acids, if they are. So, this is not the only the example, only such carboxylic acid which will have the hydroxy substitution at alpha or beta position can be used as a mixture. Will acetic acid work if we just put it? Will acetic acid work? Acetic acid would not work. Why would it not work? Because it is not a hydroxy acid. Okay. So, these hydroxy acids where the hydroxyl group is near the carbonyl group of the carboxyl group, then they can help in making complexes. That way they will make a complex and the ionization therefore will become easy from the whatever salts that you may have, metal salts, it could be sulfates or chlorides of metals. So, that is how the mixtures of metal salts and carboxylic acids can help, right. Okay. Then we have another type of a catalyst which we call as a phase separation catalyst. The typical characteristics are like this. If you plot the concentration of the catalyst, the log concentration of the catalyst and measure pH, one sees this type of a curve. That means, at some critical concentration, the pH suddenly changes. Why does it happen? Because there is, at this particular thing, there is a phase separation. And why will the concentration change? Well, when you are drying a fabric after padding, the water evaporates. So, concentration of the chemical is going to change. Is that right? If that happens, one of the salt may precipitate, one part of the salt may precipitate, and suddenly the pH again starts to decrease. That means, it becomes more acidic. So, why would anybody be interested in this? Again, same thing. During drying, it is very high pH kind of acidic pH. When it behaves, let us say, like a weak acid, as the drying takes place, it starts behaving as a strong acid or pH reduces, and so one can avoid degradations. All right. Some of the examples of these types of catalysts belong to magnesium dihydrogen phosphate, aluminum dihydrogen phosphate. They can act in this manner, phase separation. Let us say what is the mechanism. So, if you have normally a solution, let us say, of magnesium dihydrogen phosphate, at equilibrium it may contain magnesium ion, of course, it can contain some proton, it can contain H2PO4 ion, it can also contain HPO4 ion also. So, these are the types of ions, anions which and cations which will be present in the solution at a certain concentration. Obviously, because we have taken dihydrogen phosphate, this predominates, and so it behaves like a weak acid at this time, and so the availability of proton, as we talk about, is proportional to the concentration of a proton, therefore, is proportional to because weak is like a weak acid. So, it is square root of this. Let me just see if I can make it more clear. Because a weak acid, therefore, it behaves like a weak acid. Let us say what happens when we start drying, that is, the concentrations, water goes out, the concentration of the whole system, catalyst system, starts increasing. So, as the drying takes place, at a typical concentration, less soluble salt, that is magnesium hydrogen phosphate, precipitates. All right, and then the equilibrium shifts. So, it is the second rate constant, let us say which is this type of an equilibrium. Is again established. So, more of this H2PO4 will now get converted to HPO4, and so that more hydrogen ions will now start generating. This is the second equilibrium constant, because the salt started precipitating, therefore, this will start again giving more and more of protons. And if we consider that the solubility product of this compound is S, and if we take this equation 1 and then equation 2 and then substitute this, we will get and considering that under general circumstances the concentration of magnesium ions is going to be half of the concentration of dihydrogen phosphate ion, then this can become square. Look at the previous case, it was proportional to square root. The hydrogen ion concentration was proportional to square root, and now it is proportional to square. That is how suddenly it becomes more acidic. That is the way a phase separation catalyst works. So, what is the mechanism finally? So, there is, in a way, we have precipitation of a phase. In this case, this was hydrogen phosphate, magnesium hydrogen phosphate, less solubility, precipitates first. Then the dihydrogen phosphate starts releasing more proton suddenly because something has precipitated at a particular concentration, and so phase separates, acidity increases, and so they are also very efficient compounds which reduce degradation. Another interesting group of compounds are called self-limiting catalysts. Self-limiting catalysts. Now, self-limiting catalysts, how do they work? One of the ways, one of the examples is hydroxymethane sulfonic acid. Hydroxymethane sulfonic acid, which is prepared from sulfurous acid, which can be prepared from sulfur dioxide and water. It is an equilibrium reaction which can give you sulfurous acid. This sulfuric acid, if it reacts with formaldehyde, can give another equilibrium reaction and make hydroxymethane sulfonic acid. So, this hydroxymethane sulfonic acid works like an acid catalyst, something like sulfurous acid, which can also give a proton, but is supposed to be a very efficient catalyst. Very efficient catalyst, works at low concentrations and is self-limiting. Self-limiting. What it means is that because it was an equilibrium condition reaction, so this can, as we have said, would break into formaldehyde back plus sulfurous acid which will react, and after the work is done, this can go back to SO2 plus water. They all evaporate. Nothing is left on the fabric. So, this catalyst evaporates along with water also, but at a curing temperature. So, during drying you can have the drying conditions, at curing it will catalyze because of sulfuric acid being produced, then the formaldehyde, the SO2, H2O, all of them will evaporate, nothing will be left, and theoretically they say you do not have to wash, because in all cases, at least even if there is a 100% cross linking, whatever catalyst that you have used, you may not like to continue with the catalyst, and people therefore have to wash to remove the catalyst or unreacted monomers, unreacted cross linking agent. So, therefore, it is called self-limiting. The problem? Of course, the gases are evolving. Sulfur dioxide, you may not love it, water you do not mind, formaldehyde that is coming out, which has to be handled. So, you will have to have some type of a arrangement so that these gases are purged before they go out. That can be an issue, but otherwise they work pretty nicely. Strength losses are less, and you do not need to wash actually, because there is no catalyst left also. Another compound in this category is chlorohydroxide based systems, which are of various salts that can be used, and aluminum is one of them. So, aluminum chlorohydroxide, sometimes also known as basic aluminum chloride. You remember, aluminum chloride by itself is highly acidic. If you look at this compound, is highly acidic, and as we said, we like to use as a metal salt magnesium chloride rather than aluminum chloride. Okay. So, to reduce this reaction, in fact, when somebody says that there is a theory which says, well, aluminum chloride does not dissolve in water, but almost reacts with water, becomes aluminum hydroxide, and HCl can come out, and so on and so forth. The unlike just dissociation, the aluminum lying one of and chloride lying on the other side. But if you want to reduce this activity, one of the ways is to produce hydroxides of this. But if you look at aluminum hydroxide, it is not a very useful compound, it just precipitates. So, in between this, what we have compounds which can be, in some sense they have chlorine ion as well available, and hydroxyl group also available. And so, one of the ways in which various series of hydroxides can be produced with different pH ranges, once you have a certain ratio of chlorine and hydroxyl group, then you will get a different kind of pH. For example, if suppose you have a thing which says aluminum to hydroxy group 5 Cl1, it's kind of an association, right. So, more of hydroxyl, less of chlorine. So, difference from it is not hydroxide, it is not, obviously chlorine has been reduced quite a lot. So, compounds of these kind where this could be aluminum N, hydroxide M, chlorine 3 N minus M. These type of compounds are called the chlorohydroxides, and based on this ratio they can be mildly acidic. Therefore, sometimes they are called basic aluminum chloride, otherwise they could be highly acidic aluminum chloride, but it is a basic aluminum. So, you have replaced a good amount of chlorine and substituted with hydroxyl group. They have excellent buffering capacity and therefore, pH is controlled. The metal salt will be available when required in a limited capacity, would do the catalysis, and because they are mildly acidic quite, and so some people may suggest you need not wash, but that does not mean that there is no aluminum left on the fabric. Chlorine may go, hydroxide may be there. So, just a suggestion, but people may like to work otherwise also. How much catalyst one should use? So, you can understand what is the interest. Interest is cross linking, and therefore, the ratio or the amount required would be based on the efficiency of the catalyst, of course, and the resin that is being used. Instead of defining it that we define on the weight of the fabric or in solution, we say how much resin you have used, and based on that you would define how much catalyst we require. Approximately 8 to 12% on the weight of resin, sometimes it is cross linking agent also known as resins, right. Why? Because our aim is to only cross link, and therefore, they must be in some way equivalent to what is required for cross linking reaction. In a typical bath, finished bath, you may have many agents including the cross linking agent, the catalyst, you may have a wetting agent, you know why we have the wetting agent, and sometimes some people can add softener. What is a softener? Whatever, we will learn about it later, but at least the word says that it is going to make fabric little softer. And why we are interested? Because we just understood that by cross linking the stiffness of the fabric increases, okay? And so you add softener to compensate that, or maybe make it more soft also, and that is how it goes. So, what have we learnt? We have learned that we have Bronsted and Lewis acids, and they have mechanisms of catalysis which is similar but different. Organic acids and metal salts can be used synergistically to increase the efficiency of catalysis, maybe even reduce the temperature of curing. Which acids? Hydroxyl or hydroxy substituted carboxylic acids. Phase separation catalysts, we talked about mechanisms, we have learnt how they work by separation of phase, self limiting catalyst which evaporate at the end of the reaction, and pH controlling catalysts which are the, and one of the examples is like basic aluminum chloride. You may go to your lab, check out whether these kinds of catalysts are liquids or solids, whether they are hygroscopic, check what is the solubility in water, and maybe you like to check the pH of a 1% solution of acid, what is the pH level of different catalysts that we have just discussed. So, we stop here and we take a next topic in the next lecture, which will also be related to cross linking agents, but of different types of cross linking agent. Thank you.